In this video, we're going to look at how we solve circular functions. We'll start by covering how we solve the general solution to circular functions, and then we'll look at how we solve circular functions where the domain is restricted. Let's get into it. Let's start by finding out how to solve the general solution of a circular function. This is a very typical style of question that you might be asked in your tech-free exam. We'll start with a simpler version just so we can follow the process, and then once you get confident with that, we'll look at some more complicated versions. This is the process that we'll be using to solve questions in this style. Let's run through it. The first step is to rearrange the equation into an exact values expression. As a refresher, here's the exact values that you'll be expected to memorize. The goal is to rearrange the equation until we can get one of these exact values. In this particular instance, we can divide both sides by 2, thus obtaining the expression sin x equals negative root 3 on 2. This is one of our exact values. The next step is for a more complicated version of this question. This step handles the case where the circular function is a composite function. For math methods, we can consider a composite function to be any function that has anything other than x in the input variable. For example, sine 2x would be a composite function because it isn't just x in the input. In this case, we just have sine x, so we don't need to worry about this substitution. We can safely skip this step. The next step is to find all solutions to this equation in one revolution of the unit circle. Remember that sin x gives all the y coordinates in the unit circle? This means if we want to solve sin x equals negative root 3 on 2, we need to look at all the y coordinates. As a quick shorthand, we know that y coordinates are negative when they're below the x-axis. And since we're looking for the solution y equals negative root 3 on 2, we only need to look below the x-axis, or the bottom half of the unit circle. And when we do, we'll see that the solutions occur at 4 pi on 3 and 5 pi on 3. Okay, well, we have our initial solutions, but circular functions will continue on forever unless we restrict the domain. If we were to go around the unit circle one more time, this would be the same thing as adding 2 pi to our previous solutions, which would give us 10 pi on 3 and 11 pi on 3. You could even go backwards around the unit circle by subtracting 2 pi from each solution, and that would give you the solutions negative pi on 3 and negative 2 pi on 3. The common factor here is this 2 pi term. This is where step 4 comes in. Instead of writing every solution by hand until the end of time, what you can do instead is add 2 pi n to your previous solutions, where n is an integer that could be positive or negative. How does this work? Well, let's run through the scenarios. So if n equals 0, this just gives us our initial set of solutions. If n equals 1, this gives us what happens when we go around the unit circle twice. If n equals negative 1, then this tells us what happens when we go through the unit circle backwards. N could have any integer value from negative infinity all the way up to positive infinity. That's what makes this the general solution. It encompasses all possible solutions to this circular function when there's no restriction on the domain. And just before we move on, step 5 is only applicable in those more complicated scenarios where your circular function is a composite function. We'll look into that scenario next. Okay, well now that you've got a feel for the process, let's look at something just a little bit harder. This came from the VCE 2021 Tech-Free exam, but there are plenty of questions like this, so this is a good one to get used to. Like before, the first step to these kinds of questions is to rearrange the equation until we get our exact values expression, which we can do by dividing both sides by 2. Now this is where step 2 comes into play. Sin 2x is a composite function, so to make life easier for us, what we're going to do is replace the input with u. This allows us to solve this expression in the exact same way that we did in the first example, but this time we need to be mindful that we're writing u instead of x. Looking at the unit circle, we need to find all solutions to sin u equals root 3 on 2. And when we do, we find that our initial solutions are pi on 3 and 2 pi on 3. Again, be mindful of what you write for your solutions here. If you're in an exam situation, you'll be expected to write u instead of x here. Moving on to step 4, we're just going to add 2 pi n to our previous solutions. Nice and simple. Now for step 5. At the start of our question, we were told to find solutions in terms of x, not in terms of u. So what we're going to do here is replace our substitution, u equals 2x, back into our solution set. Then we're going to rearrange for x and get our final set of solutions. When you're doing this rearranging, don't forget that 2 pi n is still part of your solution set. So if you need to divide both sides of the equation, then you also need to divide 2 pi n. And that's all there is to it. Sometimes in your exam, the circular function will have a restriction on its domain. The process of solving this kind of circular function isn't much different. Here's the updated process. Let's run through it. This question here came from the VCE Tech 3 exam from 2022. The first step, as always, is to rearrange this expression until we get an exact values expression. The next step, we're going to apply a substitution because our circular function is a composite function. This is where a lot of people get caught out. When you do this substitution, you also need to apply it to the domain. The original domain was written from x1 to x2, but since we've rewritten our equation to be in terms of u, we need to write a new domain from u1 to u2. Well, how do we do that? Well, we need to look at what our substitution was. In this case, u equals 2x. So if we want to rewrite the domain in terms of u, all we need to do is multiply the lower bound and the upper bound of the domain by 2. Multiplying 0 by 2 just gives us 0, and multiplying 2 pi by 2 gives us 4 pi. The next step is to find all possible solutions to sine u equals a half in the domain from 0 to 4 pi. Looking at the unit circle, we can see that sine u equals a half when u equals pi on 6 or 5 pi on 6. Now that we have our base set of solutions, we need to look at all possible solutions within our given domain of 0 to 4 pi. We usually do this by looking backwards and then looking forwards. We go backwards by subtracting increments of 2 pi, and we go forwards by adding increments of 2 pi. Our lower bound is 0, so if we were to subtract 2 pi from our base solution set, this would go outside of the bounds of our domain, so we don't need to worry about any possible negative solutions. Our upper bound is 4 pi, and if you recall from the unit circle, this actually means 2 full revolutions of the unit circle, since one revolution is completed in 2 pi. So an upper bound of 4 pi means that there is still room for one more revolution around this unit circle. We do this by adding 2 pi to our previous sets of solutions, thus getting the new solutions 13 pi on 6 and 17 pi on 6. Now that we have all the solutions within the domain, we need to rewrite them in terms of x, because again, the question is expecting values in terms of x, not in terms of u. So we're going to substitute u equals 2x back into our solution set and divide both sides by 2, thus getting everything back in terms of x. Notice how all of our solutions of x fit within the domain 0 to 2 pi, as was previously stated by the question. If your solutions are outside of this domain, then it should tell you right away that something has gone wrong in this process. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it will take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.